Hi, my name is Sherhoz Ahmed, and in this video we will gonna discuss a topic of IP physics, that is electricity. So in the beginning we'll start discussing about charge. So charge can either be positive or it can be negative. So let's suppose we have a positive charge over here and we have a negative charge over here. So there's a property of the charges that the opposite charges attract each other and the similar charges or the same charges they repel each other. So if we have the opposite charges, they will be attracted towards each other, and if we have the same charges, they will repel each other. So if we have two positive charges, they will repel each other. If we have two negative charges, they will also repel each other. But if we have one positive charge, one negative charge, they will attract each other. So this is the property of the charge, that the like charges repel each other and the unlike charges attract each other. And our current flows due to the flow of charge. So I can relate the current with the charge as well. So let's discuss about the current. So current is basically, it is the rate of flow of electric charge. The rate of flow of electric charge, that is current. So I'll say that current is equal to charge over time, where we represent current with a symbol I, and we represent the charge with symbol Q, and we represent time with symbol T. So it will be like I equals to Q over T. So now let's differentiate between the conductors and insulators on the basis of the charge. So let me just write down about the conductors. So conductors, we can consider an object to be a conductor if it allows the charge to flow through it. Okay, so for the conductor I can say an object considered to be a conductor is considered to be a conductor if it allows the charge to flow through it. All right, and now let's discuss about the insulator. Okay, let me just give you some examples. For example, copper. In the copper, because copper is a metal, or most of the metals, they have free electrons available, and the electrons have the negative charge on them. So those metals, because they have the free electrons available, so they let those electrons move from one point to another. So that's why the current flows through the conductors and the charges are able to move. And one more thing that I want to tell you is the amount of charge on one electron. So let's suppose this is a strip of copper where we have so many electrons and they are free moving electrons. So when current passes through this object, these electrons can move from one direction to another, but the charge on one electron will be equal to the charge on one electron will be equal to 1.6 times 10 to the power of negative 19 coulomb. So that will be the charge on one electron. So after the conductors, let's discuss about insulators. All right, so insulators the objects that do not allow the charge to pass through them. That do not allow the charge to pass through them, they are called the insulators. So that is the difference between the conductors and the insulators. The conductors allow the charge to pass through them, but the insulators they do not allow the charge to pass through them. So that's why there's no current flows through the insulators and current flows through the conductors. Alright, so after this one we have to discuss about the concept of electric fields. Alright, so electric field is basically let's suppose we have a positive charge and these are the electric field lines that are moving away from this positive charge. And now we put another positive charge within this electric field. Now this positive charge will experience some force of repulsion due to this charge. Okay, so we can say the region or space in which a charge can experience an electric force is called the electric field. If it is a positive charge, it will experience a force of repulsion. If it's a negative charge, then it will experience the force of attraction. So I can write it over here. The region or space where a charge experiences electrostatic force of attraction or repulsion. Electrostatic force of attraction or repulsion. So that region or space is called electric field. So it is called electric field. Alright, so now let's draw some electric field lines. So we represent the electric field by the electric field line. So you see these lines that I have drawn over here. So electric field is represented by these electric field lines. Let me just draw some of the charges and I'll show you the behavior of the electric field lines, and we will see the points at which the electric field is maximum, some points where the electric field is less, and some points where the electric field is 0. Alright, so let's suppose we have a positive charge, we have a negative charge. So we represent the electric field lines, we represent the electric field by the electric field lines, and the electric field lines, they start off from the positive charge and they end at the negative charge. So they'll start off from here and they will end at the negative charge like this. Like this. They are starting off from the positive charge and they are ending at the negative charge. And in this direction they'll just going away from it like this. Now let me just draw the arrows. So they are going away from the positive charge and they are moving towards the negative charge. So the arrows close to the negative charge will be towards it and the arrows close to the positive charge will be away from it. Now let me just consider some points where I'll compare the electric fields that will where I'll compare the electric force that will be exerted on some charge. So for example, this is position 1, this is position 2, and over here I have the position 3. So if I place a positive charge over here at position 1, it will experience the maximum force of repulsion. If I put a positive charge over here at position 3, it will experience a moderate force of repulsion. But if I put a positive charge over here, it will experience the minimum force of repulsion. So as a conclusion, we can say that the area or the region or the space where the electric field lines are close to each other, at that area the electric field strength is more, and the area where the electric field lines are away from each other, in that area the electric field strength is less. Alright, so this is the electric field lines between the positive charge and the negative charge. Now let's see the electric field lines between two like charges. Alright, so if we have two charges and both of them are positive, so what will happen is the pattern of the electric field lines will form like this. It will initiate from positive, but because there's another positive in front of it, so it will be repelled like that. Alright, so it will repel like this, it will repel like this. So this is how a pattern of the electric field lines form for the like charges. Alright, so the electric field lines are going away from the positive charge for both the charges. It's going away, away, like that. Okay, now let me just place some the charge on some different points. So when I put the test charge over here, I'll experience maximum force of repulsion. If I put my test charge over here, I will also experience the force of repulsion, but in this case the force of repulsion will be lesser than the position 1. Now if I place a test charge at this point, now you see there is no electric field line that is being passed through this point. So at this point my electric field strength will be equal to 0, which means no force will be exerted onto the test charge if it is placed at position 3. So this is how we can draw the electric field lines, and this is how we can determine the force that is exerted on a test charge that is placed within an electric field. Now this type of electric field is called a non-uniform electric field, because the lines in some areas the electric field strength is more, in some areas the electric field strength is less. So now let me just show you a figure in which our electric field will be uniform. Alright, so let's consider a positive plate and a negative plate. They have become positive by being connected to the positive terminal of the battery. It has become positive, and this plate has become negative by its connection with the negative terminal of the battery. Now let me just draw the pattern of the electric field. So the electric field will start from the positive terminal and move towards the negative terminal. So in this case we will see the lines are equally spaced from each other, and because the lines are equally spaced from each other, so we can consider this as the uniform electric field. There we will see some curves on the edges, but within these electric fields, within these uniform plates, the electric field lines, they are uniformly spaced from each other. So now over here, when we put a charge at any point within this electric field, that charge will experience the same electric force of repulsion. So no matter I put the charge at position 1, position 2 or position 3, the amount of force that will be exerted onto that electric charge will be the same. So this is the concept of the uniform electric field. So this electric field will be considered as the uniform electric field, and the field that I drew before, that was the non-uniform electric field. Alright, so after this one I'll discuss the concept of finding out the amount of force that is being exerted on one charge by another charge, and in order to do that I have to discuss the Coulomb's law. So now let's discuss the Coulomb's law. Alright, so Coulomb's law, it states that let me just write down the definition first, then I'll write down the formula. It states that the force of attraction or repulsion between two charges is directly proportional to their product, is directly proportional to their product and inversely proportional to the square of distance between them. I know it's quite a lengthy definition, but we have to write it the whole thing. So the force of attraction is directly proportional to the product of the charges. So let's suppose there are two charges. Let me just write down the two charges. So this is one charge, I'll consider it as Q1. Here's another charge, I'll consider as Q2. So there'll be a force of attraction between these two charges, and the distance between the charges is, let's suppose, R. So the force of attraction between these two charges is directly proportional to their product, and that force is inversely proportional to the square of distance between them. So when we combine this formula, it will become F equals to, F is directly proportional to Q1 Q2 over R square. Now in order to replace this sign of proportionality, I'll write it as F equals to 1 over 4 pi epsilon naught Q1 Q2 over R square. Now this epsilon naught is the permittivity constant. Permittivity constant, it basically, its value depends on the region or space that is between these two charges. If it is air or vacuum, then its value will be 8.85 times 10 to the power of negative 11 or negative 12. And when we solve this whole thing, we will replace this whole thing with a simple constant, and that constant will be considered as K. So I'll write it as F equals to K Q1 Q2 over R square. Now this K is 9 times 10 to the power of 9. So this is the force that is exerted between, this is the force of attraction or repulsion between the two charges that could repel them or that could attract them if the charges are same or different. So by this formula we can find out the magnitude of that force. Now after this Coulomb's law, we will find out the electric field strength at any point, or how can we find out the electric field strength at any point. Before we have discussed that we can find out the where the electric field lines are close to each other, the electric field strength is more, but where the lines are away from each other, electric field strength is less. But over here we will discuss how we can find out the electric field strength. Alright, so in order to find out the electric field strength, let's understand the concept of it. So if we have a charge and it has the electric field lines going away from the charge, they are radially outwards. So these are the electric field lines going away. If we put a test charge over here, so it will normally the test charge is positive, so it will exert a positive force of attraction, repulsion. It will exert a force of repulsion onto this charge. So in order to find out the magnitude of that force of repulsion, we'll use the Coulomb's law. But in order to find out the electric field strength at that particular point, we will use the concept of electric field strength. So electric field strength says that it is the amount of force exerted on a unit charge that is placed in the electric field. Is called the electric field strength of that position, of that point. Is called the electric field strength of that point. Alright, so the formula for the electric field strength will be like this. It's E is equal to F over Q, the force per unit charge. And in terms of coulombs force, we will write it as equals to K Q1 Q2 over R square divided by Q. And once we'll solve it, I'll replace it with multiplication sign, and this will become 1 over Q. So 1 Q will get cancelled with this one. So in simple terms, my electric field strength will become equal to KQ over R square. So if I have to determine the electric field strength at any point in the electric field, I need to know the charge by which the electric field is being created, and the distance from the charge to that point within the electric field. So I'll use this formula and work out the answer. So this is it for the topic of electricity, and now we'll move on to some questions. Alright, so here we have an exam related question for the topic that we have just discussed. So it says that diagram shows the electric field lines of a positively charged conducting sphere of radius r and charge q. Points A and B are located on the same field. Explain why the electric potential decreases from A to B. So let me just tell you the formula for the electric potential first of all. So it is V equals to KQ over R. So this Q is basically the charge at the center, and R is the distance from the charge. So as you can see, at point A the distance is less, at point B the distance is more, so that distance is greater than the distance at A. So while the electric potential is inversely proportional to the distance, so you can say that the electric potential will decrease as the charge will move from point A to point B. So we'll write it over here, the formula that V is equal to KQ over R. Potential, like electric potential, is inversely proportional to the distance. Inversely proportional to distance, hence it decreases when the charge moves from point A to B. When the charge moves from A to B. Alright, so this will be the answer for part A. Now let's see part B. It says draw on the axis. Let me just scroll it down. Okay, so in this one it says draw on the axis the variation of electric potential with distance r from the center of the sphere. So let's suppose there's a sphere. This is the center of the sphere, and from here to here is the radius of this sphere. So from the center to the surface there will be no decrease in the electric potential. So I'll draw a straight line from the center to the surface. So up till this point I'll just draw a straight line because there will be no decrease in the electric potential. Now when the charge moves away from the surface, the electric potential will start to decrease exponentially because it's KQ over R. So the curve will look like this. There you go. Okay, so this is how the variation of the electric potential with the distance will look like. Now this is done. Let's see part C. Alright, so in part C it says a proton is placed at A and released from rest. The magnitude of work done by the electric field in moving the proton from A to B is this much. Point A is at a distance of this from the center, and point B is at a distance of 1 times 10 to the power of negative 1 meters from the center of the sphere. Calculate the electric potential difference between points A and B. So in simple words, electric potential is equal to work done per unit charge. Because it's a proton, so the charge on the proton is 1.6 times 10 to the power of negative 19, and the work done is already given in the question, so that is 1.7 times 10 to the power of negative 16 joules. So the potential will become equal to work done per unit charge, so that will be 1.7 times 10 to the power of negative 16 divided by 1.6 times 10 to the power of negative 19. So when we'll solve it, we'll get, let me check. Alright, so when we'll divide it, we'll get 1062.5 and the unit will be volts. So this will be the work done. Now in the next part it says determine the charge Q of the sphere. So what we do is we have the potential difference between point A and point B as 1062.5. So we'll say that the potential difference of A minus the potential difference at point B is equal to 1062.5. Okay, so VA will be like this: KQ over RA minus VB is KQ over RB, where RA is the distance from the point A from the center, and RB is the distance of point B from the center. That is equal to 1062.5. So I'll do some working over here. So I'll take KQ as common, and it will be like 1 over RA minus 1 over RB equals to 1062.5. So from here I'll make let me just find out the values. So it'll be like 9 times 10 to the power of 9 times Q times, now 1 over RA is basically this much. Point A is 5 times 10 to the power of negative 2, and point B is 1 times 10 to the power of negative 1 is equal to 1062.5. So from here I'll make Q as my subject, and it will turn out to be 1062.5 divided by 9 times 10 to the power of 9 times whatever is the answer of this whole thing. I'll just put that into the calculator and get the answer. So from here I'll get 10 as the answer. Now I'll just put this whole thing into the calculator and we'll get the charge. So the charge on the sphere that I'll get is 1.18, or because I have to write that in two significant figures, so I'll write it as 1.2 times 10 to the power of negative 8 coulomb. So this will be the charge. Now in the last part it says the concept of potential is also used in the context of gravitational fields. Suggest why scientists develop a common terminology to describe different types of fields. So they have, we'll just say that to highlight the similarities between different fields. So this is the answer for part D, and this is it for the topic, and I hope you like it. Thank you.